The information contained in these presentations should be considered as general guidance and not engineering advice or services for any particular applications. The opinions expressed are solely those of William G. Beasley and should not be construed to endorse or condone any product, practice, or method. Much of the material was recorded live in a classroom setting and as such may contain unintentional errors and mistakes. In all cases where services to the public are concerned, consult a professional engineer licensed to practice in your particular state or country. Just for tease. Now, computer-aided design. Now, I'll tell you, this is my favorite topic because it's the one I've spent most of my career working on, is how to characterize piping systems. First of all, piping systems are distribution systems. They're really designed to distribute fluids. Because of that, they have connection points. They're like electricity. You wire stuff in the wall, every terminal is a connection point. Same for pipe. Every nozzle is a connection point. So we have ports, and we care about what they call topology, how things are connected. Ports. Every CAD system has a port concept. And you've seen it already. Every CAD system has a connection point concept or a port concept. And then we care about locating components in space. We also care about alignment. Every pipe that connects to a nozzle, every nozzle that connects to a nozzle needs to be aligned with the nozzle too. Not just connected, but aligned with it. Here's something from Bentley. I care about ports. A pipe is a two-port system. A flange is a two-port system, and if I want to put a flange on the end of a pipe, I have to tell it that this port and that port are either the same port or they are now connected. You have to have some concept of telling it that they're connected. And then I also have to have alignment. Well, first of all, let me say that this idea of attaching something, attaching a flange to a pipe is the same thing as saying your ports are connected. Ports are now identical. Like a wire, attaching a wire to a terminal, you're now connected. And if I want to have a branch, I need a three-port device. I need a main run, and then I need a branch port. And if I have a pressure vessel, I have 20 ports. Who knows? The other thing is, when I place something in space, I need 3 coordinates to get the origin placed, and then 3 more numbers to get the orientation right. I need 6 numbers to place an object in space, on top of telling it it's connected. So if I tell 2 things that they're aligned, I'm telling them that one vector in that is going in the same direction or has the same direction or an opposite direction as another vector in the other component, and they have a point in common. Like the Earth has an axis, okay? That axis is a location and 2 more numbers. The only thing you don't specify on the Earth is where around the rotation you are. So if I aligned it, I have an axis. Now, you ever see an exploded drawing of a pump? All the parts are exploded out on their axes. Those parts are aligned, but they're not connected. See, so alignment and connection are different issues. Okay, now let's talk about solids. What solids do we use in CAD systems for plants? Well, for pipe, it's easy because it's got one cross-sectional area, like I-beams have one cross-sectional area. So we use mainly a swept solid. That's a cross-sectional area that goes along a path. Okay, Superman running through the wall, bam, outline of Superman. Okay, that's a swept solid. Those are easy. For components, I have to construct them from primitives. This cone and this cylinder are connected together, and this cylinder connected together, and so on. And I join them up. I have a buildup from primitives, or I have a rotation. I have a solid rotation. So there's a swept solid, except for the structural detail. The beam is a swept solid. Here's a buildup, constructed solid geometry. Some say computational solid geometry, depending on the vendor. Here's a buildup of a T from primitives. Now here's a swept solid, a macro for a PDS. Now look here, it has an origin in the center of the valve, and then it has two connection points on either side. It's a two-port device, and they have out vectors. Here's where to connect, and here's my out direction. And so if I connect it to another flange pipe or a pipe, actually this is a socket welded valve, so if I connect it to another pipe, then the connection points have to be shared and the out vectors have to align. And the way to generate this, they just have an outline and they sweep it, they spin it. Okay, another issue in CAD models is model space and paper space. You'd like to take your dimensions for things from model space, but you'd like the size of the letters of the dimension to be in paper space. So we usually like to have these two concepts in a CAD system, model space and paper space. The other thing the CAD systems have to do is decide how they're going to handle components. Do you put all the data for a component in every time you use it? Or you just put an instance in the model and say, here lies Bill Beasley. And over here lies Bill Beasley. And over here lies Bill Beasley. And if you want to find out what I look like, you go to a database and look that up. But you just use an instance of the component. It leads to more economical design. But if you make a change to the central definition, all the instances are now going to look different. And then you're stuck. As a CAD person, as a designer, you have to maintain these libraries. You've got to make sure if I get the right answer, I've got to have the right library when I do the bill of material, the right library when I do the rendering. That becomes your job. You think you're in the design business, but you're in the paperwork, the database business. You're a data guy now. And then here's the problem. The EPC company has a master library and a client comes in. Well, we do the Shell library and the Exxon library, and then they get a Shell job in Malaysia, and now we tailor it again for the Malaysian job, and now you have all these detailed libraries. And who has to maintain that customization? You or somebody with you has to maintain that. But you get the problem. You should be aware of the problem. Now let's talk about clash detection. Here's a hard clash. That's a physical thing that's running into a physical thing. I must fix that. That's a broken path. Not recommended. But here's a hard-soft clash. Maybe I can tolerate taking that spool off every time I want to pull those tubes. Maybe I can. I don't know. Maybe hard-soft clashes you can live with, but hard clashes, there's a problem. CAD model backups, you want to back up after every significant change. I change the software, back it up. I get a new release of the software, or the client makes a change, or I make a delivery, back it up. And then always a question, what to back up? And the best answer is everything. It's always the best answer. Every answer that revolves around everything is going to be the right answer. Always say everything. This says what to back up. It really should say when to back up, because you change, you can back up after every workday. If you're like me and you're doing a for-profit job, you're backing up all the time. You don't know. You could lose your computer, it's run out of the building on fire. You don't know, so you back it up. You're in the data protection business as well.